Hello. Has everybody had coffee so far? Great, super, icy looks, bright looks, people alive. This is fantastic. I'm happy you've had coffee. I'm going to make you consensus expert if you're not already in about 30 minutes. And so this is a story about looking into consensus properties and fixing some of the properties of consensus and then stumbling into high throughput mempool and then integrating it into Celo. All right, so we're going to go from consensus to that consensus. That's the consensus fix we were looking for. And then from that consensus to a mempool, and then from a mempool to a prioritized mempool where we can figure out how to integrate transactions that are super duper urgent into a block. About me, I'm a software engineer at Instant Labs. I'm working on the integration of the Narwhal mempool directly into Celo. I've been working at Novi, Diem, Libra, on consensus algorithms before, and you can find me on Twitter. And the first thing, like the basics about becoming an expert of the consensus in 30 minutes is figuring out why we even care about consensus, right? The answer is the state machine replication paradigm. The idea that we want programs to be reliable and run the same thing in many places. We want to have many replicas for reliability, and we want to have consistency to make sure they output one single consensual thing. Okay, how do we, what are the physics of what we're dealing with? The physics of what we're dealing with is that, yeah, you need an all-to-all communication to figure out what to be consistent about in the first place, so that everybody has heard of the thing. And then you can resist up to F failures among 2n+1 nodes, which is the general consensus setting, which is, okay, we're going to have n-square communication in the worst case, and we're going to try to bring that number down. N-square communication means that where n is the number of authorities, we're going to need to have that to have messages that cross that full connectivity graph. So if your vertices are authorities, we're going to need to send all of the nodes messages from any other node. And so that's been the academic setting in which people have been trying to make consensus efficient. We can't do better than n-squared because every node needs to vote on everything that everybody proposes, and everybody else needs to witness those proposals, so we're going to have to deal with n-squared in the worst case. But can we do better? In some semi-happy case. And the answer here is leader-based consensus. So everybody has tacked on the idea of leader-based consensus because it allows you to do something magical, which is, in the bad cases, where the leader is bad, you fall into that worst case. But in the happy case, you have this picture. And so that's the reason everybody latches on leader-based consensus. And the reason here you have messages flowing on every line, so every line is an authority, that are using a leader to collect a message, vote, that's the lines that are all converging toward the same point, and then rebroadcasting that message to everybody involved. And if you think about it, that is only messages going from a leader to all the nodes and from all the nodes to another leader. And so in that happy case, as long as everything goes well, your O of n squared becomes an O of n. And so that's great, right? Except for one small detail. When you actually implement this and you actually benchmark it, you figure out that the CPU utilization has some peaks, but that's not really the problem we're going to talk about today. But you have network utilization problems. And that's the blue in this slide. And that is to tell you that today on the internet that we know today, basically sending one message to n machines means sending n times one message in terms of pure bandwidth. And so your bandwidth utilization is absolutely terrible because we don't have nodes that have a gigantic, fantastic magical bandwidth like that. And yes, some of you that are network engineers, I see eyebrows being raised, will tell me UDP. And sadly, we don't have well-developed UDP with the routers that would do the thing that we would like them to do, to have this primitive that across a one, you can actually send a message in a cost of one. So to summarize all those problems of leader-based consensus, you usually run consensus not alone. You run coupled with a mempool from which you select your block proposals. Your leader selects the stuff that they would like to put in a block, broadcast it to everybody, Everybody executes the transactions, validates that the leader suggested his execution works, and then sends that back to all the to the next leader or the same leader, depending on which protocol you're talking about. And the problem is that your network, there's two problems. The one we're going to mostly focus on today is that your network is saturated at the leader, and that nobody else is meaningfully using network during this entire picture. So on the way of doing this, we'll see that we'd like to better use the network at all the other validators and solve this over-utilization in the leader. But have you noticed that transactions are submitted twice? That's a thing that is actually non-obvious to see, but one of them is in the mempool, right? In the mempool, you're sharing with everybody, including the leader, all the transactions that could go into the consensus. And then you select those that should go in the consensus on this round, and you broadcast that to everybody. But they have a copy already? In fact, the insight that they had a copy already is already present in Bitcoin. Bitcoin does short hashes to make sure that when they retransmit transactions as part of a block proposal, they retransmit as few bytes as possible from that transaction to avoid retransmitting it twice. Okay, turns out we're going to look at leaderless consensus. That sounds like a good way to eliminate the leader as a bottleneck. And so leaderless consensus is actually an old thing. You might have heard of it because of a consensus protocol called Hashgraph, which is the popular one, but that stuff is as old as state machine replication. It's as old as work from the 90s from Moser and Ilya Smith, at least. And there's a long history you can read at your leisure later. And what I'm going to talk about is the latest work in this area called Narwhal and Tusk. And Narwhal and Tusk is the systems paper, the implementation paper, the stuff with all the experimentation, the physics, the diagrams, the benchmarks of a theory paper called All You Need Is Tag, which comes from the Brian Fowler PFL line of work. So this leaderless approach, of which we're going to focus on the data availability optimization, those network optimization, the very practical-oriented approach to things, has a couple of interesting ideas. A couple of them we're never going to talk about in this talk, but buy me a beer later and we can have those discussions. But the one I'd like you to notice today is it's symmetric, of course. It's leaderless, so there's no special leader. There's no denial of service, adaptative denial of service of the leader that would be meaningful. All the machines work in concert, and that kind of organically draws you to build protocols that scale a lot better and that have a nice performance under fault, because if 10% of your machines are down, well, you only lose 10% of the network relatively organically. Okay, so now let's look at what Narwhal actually does. So the latest and perhaps simplest version of a DAG-based consensus protocol tries to create blocks. And we're going to call them blocks, but the Narwhal Tusk paper is going to be called to call those blocks. Don't think of them as consensus blocks. In fact, I'm going to rename them collections in about 2 slides. So those are not your consensus blocks. Think of them as small collections that are small sequences of transactions. The transactions come in at all the nodes, and those nodes are organized in asynchronous rounds, those which are, again, not the rounds of your consensus. But the idea is they all function in concert and know, oh, okay, on this particular round, I'm going to make a proposal. And everybody does a proposal. It's a multi-proposer system. They broadcast that proposal to everybody and get back votes. Anybody that gets 2f+1 votes has a Byzantine-resistant proposal that has been validated by everybody in the network, and sends back that certificate, those 2f+1 votes, to broadcast it again on the network so that everybody is convinced that their proposal works. So far, so good. But what we're really reusing is the edges, the arrows you're seeing on this graph. Those arrows are back-pointing arrows pointing to the blocks that occurred on the prior round. Those arrows are the meat and butter of DAG-based consensus protocols. And I tell you that transitively, you have, through your block proposal, acknowledged that several other blocks from the prior round were also valid. And that is where you get a lot of throughput. because that transitive acknowledgement allows you to not only build consistent proposals on every round at every single node, but they allow you to build a DAG. And a DAG is a big graph data structure where here the authorities A, B, C, D are in column. The rounds go from bottom to top. So the arrow of time goes from bottom to top. And on the happy path, every authority proposes one collection per round and acknowledges the collections from the others. Those acknowledgements are literally hash pointers in a single proposal. And that means that they are reproduced identically on every authority that has a copy of those blocks. And then it's just a matter of engineering the data availability behind this. So we have blocks at every single authority node. Every single node's proposal is transmitted throughout the network, and everybody has a copy of that graph. What can you do with a copy of that graph? Well, you can build a mempool. It turns out you can build a consensus protocol, and we're going to look to that in the next slide. But the fun part is that this, in a context where we work with an external consensus protocol that consumes those nice collections, is collections. Each of those collections, remember they're signed, comes with a certificate of availability. That is, it comes with 2 F+1 signatures, and 2 F+1 signatures, of which there are at least F+1 that are honest, tells you that the majority of the honest nodes are ready to sell that stuff. In fact, in practice, the majority of the honest node already has a local copy of that stuff. All of this is traceable. There's nice properties like chain quality that I'll refer you to the paper to explore. And on top of this, we can scale out each authority to maximize the database, the bottleneck of I/O, and the network latency. And in fact, this is what you're seeing on the right, which is that one primary worker is assembling some worker batches into their collections on every proposal. And that makes sense, because you're probably, whether you know it or not, already running proxies in front of your node. Why? Because that's where you submit transactions. If that's where you submit transactions, even if you submit them to full nodes, etc., you're inherently running from a network point of view proxies if you are running in front of a gossip network. So your peers are just giving you some of their network bandwidth to tell you about transactions. This is quite fast. Just this works really well. So in this diagram, you're seeing full network benchmark that are reproducible. I can point you to an open source repo where you can run that on your own for a couple of bucks given to Amazon on several regions. There are several curves. I'm not going to explain them all, but you're going to see Narwhal and something on the right, and then Tusk. Tusk is our homegrown consensus algorithm that we're going to talk about very, very briefly. Narwhal dash something means that we're running Narwhal with an external consensus algorithm that is leader-based and picks some block proposals out of the mempool. And then batch hot stuff is the hot stuff consensus algorithm, but without the Narwhal mempool, just by running hot stuff ahead of time to run collections. So basically what the blue line tells you is that even if you're running with a consensus algorithm that is leader-based, the fact that you're compressing a lot of transactions into collections that you can address by pointing to collection hashes, already gives you a lot of throughput. Okay, I told you there was a consensus in there. It's true, there's a consensus in there. You can look at the paper if you want to look at it. It's a zero message overhead a consensus that can be built on top of Narwhal by basically using the fact that DAG walls are deterministic and that you can make a proposal out of a DAG wall coming from one particular vertex in the DAG. It has nice properties that interest the consensus experts. Some of them are not so nice and require a bit of engineering, like the random coin. We have a version without the random coin if you don't like that. But what does it mean to integrate the Narwhal mempool with something like Istanbul? That I've told you about this external consensus algorithm for a while. This is exactly what this means. As long as you are within a reasonable number of nodes. And this picture is entirely backwards compatible. So what this means is you submit your transactions directly to Narwhal node in the Narwhal mempool. You may or may not decide to scale your Narwhal nodes to have some workers that receive transactions independently and are completely fallible. If one of them dies, that's not the end of the world. The Narwhal mempool gives you collections. Those collections are tiny, addressable, hashable blocks, mini blocks of transactions. And so now you don't need to explain transactions in your block proposal. You can just refer to collections themselves. What that concretely means is that your block proposal is tiny. You run that through consensus, for example, Istanbul. Istanbul orders, Istanbul gives that to the leader. The leader selects their block proposal, sends that to all the validators, and the validators, seeing a block composed of collections, says, yeah, I know how to interpret all of this. I'm going to look to my local mempool, and I'm going to expand this block like a big decompression function into a huge block with many transactions. Now you have the raw block, and the raw block, when you have the raw block, you're done. That expanded block is the normal Istanbul block that you would normally vote for. You finish your consensus voting, the ceremony of accepting that particular block, execute it, and you're finished in exactly the way that you would do that normally. Okay, so that basically tells you we have a high throughput mempool, we put it in front of Istanbul, everything goes faster, and you transmit blocks much more efficiently. But how do you come to a good block proposal? Coming to a good block proposal is a thing that is actually counterintuitive. So the core insight from Narwhal is that the contents of a collection are the same at all validators. That allows you to receive messages in terms of collections. They reference them into messages that talk about transactions. The core insight for Tusk is that the DAG walls are identical in terms of every NS node. What if we could compress our block proposal even more, and instead of listing collections, we could list just one collection, and then let everybody figure out, through walking the DAG, that this implies many collections, and the many collections can then be their reference into transactions, and then you have your raw block, and then you finish the ceremony of everything, and you have your consensus, right? Okay, so we've reduced many transactions to many collection hashes, and now we want to reduce many collection hashes into one single collection hash. And that lets us define a mempool that just has 3 operations. You started a walk, and when I say walk, I mean a breadth-first search, depth-first search, the usual basic graph theory 3 walks that we deal with in Algorithms 101. Pick your favorite, you can customize it. The point is everybody has the same graph, and the walk is deterministic. You can do that read on every single validator, collect the collections pointers. You have a call to get collections that lets you expand that into transactions. And you have a call to remove collections that tells you, hey, by the way, those collections you gave me earlier, they are now part of a committed block, okay? They're in ledger storage. They are part of my chain forever after. You don't need to store that anymore. This is no longer part of the mempool. Okay, so now we can do block proposal with just one single collection, and then a DAG walk. Aren't we happy? Turns out we're not happy. Here's the reason. Most everybody in their mempool actually works in terms of priorities. They don't work in terms of graph walks. A graph walk, like a depth-first search, would tell you, I'm an authority, let's start a DAG walk, and in priority, first put my collections, because I'm node number 42 and I know better, and then we're going to walk the collections from the other guys in the network. If I do a breadth-first search, I'm doing node rounds, so I'm focusing on history here. So we're going to select the collections that came in at round 1, and then the collections that came in at round 2, and the collections that came in at round 3. So that's high throughput. That will get you big blocks with big transactions committed really fast, but it binds you to a FIFO. you're going to basically empty your mempool from the bottom to the top. And that's actually something we thought we needed in Narwhal. So here's what happens. You receive messages from the consensus telling you, remove those collections, I have completely committed all of this, you don't need to store it anymore. And then number two, another message tells you, remove those collections. I'm completely done, you don't need to store those anymore. And then you start the recausal to start figuring out what is in your mempool. So you start at A4, you're probably going to continue with like A3, A2, because they haven't been removed, C3, C2 aren't removed either, but then the rest seems to be removed if I have my stuff figured out correctly. And so everything is great, but what if your removal could create a graph cut? Your removal can actually separate your DAG into two parts of the graph that are not reachable from each other. So you start a recausal somewhere, you can't reach the other part of the graph. Turns out to solve this, you do a little bit of algorithmics based on an old data structure from 1975 called the union find, and that stuff allows you to basically reflect the idea of the union find is that they have this discipline called path compression that can be implemented in 12 ways. The simplest is on the slide, which recognizes that a node is only useful for its connectedness information. It doesn't need to exist as a node anymore. So you can even have a deterministic representation of your graph that maintains that connectedness information and breaks out of the FIFO priority order for transactions. So we are now a full-fledged mempool where you can transmit, you can select what you want in a block proposal anywhere in the graph. You can remove that out of the mempool anywhere in the graph, and you can still have block proposals that are extremely compact because they refer to essentially one single collection at a time. That's it. Thank you very much.